So this is an important session for the Society. As many of you know, the Society takes great pride in awarding PhD theses and outstanding young colleagues. This is done through a nomination process where people submit their nominations, and the President appoints a committee that evaluates each nomination. And once they make a decision, they are announced. Before 3 years, we used to offer the PhD awards only once every 3 years, but since the field is growing, we have now decided to offer it every year. So that is the reason why you see 3 PhD awardees here. And this year we also had an unusual but a good situation that the committee decided that we'll have a joint winners for also the Young Scientist Award, essentially. That is for a young scientist with outstanding publications. At this point, I should also thank Paulo, Alexandra, and the organizing committee for waiving the registration fees for the award winners. And the Society supports them through a prize award and also some a travel grant. So it is, I'd like to make 2 points. Colleagues that you have, students and young researchers, please nominate them. Only if they get nominated, they get considered, so please nominate them. It's a fantastic opportunity. And the next one is for all the awardees. With great awards comes great responsibility. So we look forward for your continuous support to the Society and to pay it forward to other young people. So please engage yourself with young people. They really look up to all of you as future leaders in this Society. Conor, over to you.
Thank you all for coming to my talk. Before I get into kind of the meat of the presentation, I'll just kind of give some background information on the work of my thesis to provide some context for the scientific question that we're trying to answer in this work. So my work was primarily focused on adsorption-based carbon capture and storage. This being a fundamentals of adsorption conference, I don't think I need to go into too much technical details on what that might look like, but suffice it to say, the success of deploying these technologies is contingent on the choice of a high-performing adsorbent, which can selectively capture CO2 over other gases in a mixture. Now, there are several classes of materials that we can consider at this stage. One of the most, one of the popular ones that we're looking at right now are things like metal-organic frameworks. So we can, due to their modular nature, we can kind of deconstruct these materials and then into their constituent building blocks and then reform new materials. And this capacity for customization points towards an almost infinite number of ways that we can fine-tune these materials for a given application. So looking at things like capacity and selectivity and kinetics and things like that. Now, these materials have to be deployed in industrial adsorption processes or industrial adsorption columns where we can cycle between adsorption and desorption conditions by changing the conditions of the cycle. So how this is designed and where it's placed geographically in the world will affect the performance and indeed the capture cost. And so what this tells us is that adsorption carbon capture is inherently a multi-scale, multi-objective design problem where we're competing with different objectives at both the material and process levels of description. Now, a problem we have in this field, or maybe a benefit, depending on your look, is that we're actually quite spoiled for choice. With such an expansive chemical landscape, it's not really feasible to perform a random search. And so what we have to rely on is kind of more advanced computational techniques. And so kind of current efforts in this domain rely on these multi-scale simulation workflows, whereby we start from a database of materials and then we can predict properties of the material relevant for carbon capture applications. And then properties at this level that are predicted can be passed on to more advanced process models where we simulate conditions intended to replicate the real industrial process. The objective here is to kind of find combinations of the process parameters that give rise to the best performance of a given material in this cycle in coordinates of either energy and productivity or maybe some other metrics. And machine learning can be utilized at pretty much every intersection of this pipeline, and so maybe more appropriately it would be called the ML-aided multi-scale simulation workflow. And if we use this approach for enough materials, we can produce a so-called rankings list where we can say that material A is better than material B and so on. Now, this is really nice and attractive in principle, but as it turns out, this kind of workflow hasn't produced a material to date that has been scaled for industrial applications. And so in reality, there's a lot of problems that occur between conception and application, including but not limited to kind of the quality of the materials that you sample, as well as their properties, and in how information and uncertainties propagate from one simulation level to the next. And so my thesis generally falls under the umbrella question of how can we make these workflows or processes more reliable and robust. And the three main questions that I asked was, how does experimental uncertainty impact the performance of our processes, and our process level ranking is contingent on the choice of particular molecular force field, and then finally, are there better materials to sample from? Now, the first two questions I've kind of already given talks on before, and if you're more interested, then you can have a look at some of our other publications. But in this presentation, I want to focus more on this last question: are there better materials to sample from? And to provide context for how we aim to maybe address that question, we have to look at this particular intersection of the pipeline, where we can use things like neural network models to predict the properties of materials. Before we can proceed, you kind of need some rudimentary understanding of how neural networks work and how they learn from data, but effectively they're just composed of neurons which apply a linear transformation to some input data, let's call that X, using some learnable parameters, these weights and biases given by W and B. The objective is to learn a mapping between the input and some desired output, and sometimes that mapping might be not really straightforward, so we can introduce some non-linearities to our system using activation functions, which could be something like a hyperbolic tangent or a sigmoid function, something like that. And in practice, we have neural networks with many layers. Let's call that L. So we can say that the activated output of the finer layer will be taken as our predicted output for the model. Let's give that y hat, which is given by the following expression. And then we can define a cost, or we can compute the error or define a cost for this prediction for the model using something like a mean squared error. So it's just the difference between the actual value and then the predicted value. And then for many data points, the objective is to find the combination of the weights and biases that give rise to the lowest cost or the lowest overall error, right? And in order to kind of find the optimal combination of weights and biases, we have to understand how sensitive the cost function is with respect to those weights and biases. So in other words, using something like backpropagation. And once we've trained our model to predict properties of materials, we could go on to do accelerated high throughput screening, which is fairly common. But maybe a more interesting question to ask would be, okay, what happens if we go in the reverse process and we are interested in finding for a given property value, what is the optimal X value, or can we optimize our input towards a desired property value? And this is in essence the idea behind deep dreaming, which is just an approach towards inverse design of materials. So in the forward or training process, we have a neural network, we have a property predictor, which has been where you train it to predict a property by updating the weights and biases using that derivative of the cost function, using a fixed feature vector as your input. And then once we've obtained that optimal series of weights and biases, we then invert the architecture and then freeze the weights and biases, define a target property value, and then take the derivative of the input with respect, or derivative of the cost with respect to the input and optimize it like this. The end result, or the hope, is that the optimized representation will decode to a molecule or material with improved functionality. In this case, that's the inverse design principle. In order to do that, you kind of need a way to encode materials that is differentiable, such that you can use gradient information in order to update the input. And for us, that kind of encoding looks like this. We have a MOF, which we can abstract to the level of structural building units and maybe a topology. And then we can encode the chemistry of those building blocks using a molecular string representation. In this case, we use something called selfies, which is just it's just essentially a vocabulary of identifying different chemical entities. or entire chemical substructures. So at the top, I don't know, it's not going to work anyway. We have particular tokens that represent certain chemical substructures, and the unique collection of those tokens represents our alphabet, our vocabulary, right? And then we also encode some of the topology information using these RCSR topology codes, which then comprises our complete MOF string. Our focus for now is on linker optimization, which is the area with the greatest capacity for customization. But we have to convert these non-numerical features into something machine learning friendly. So we can use something called a one-hot encoding, which is effectively just taking those tokens and creating a bit vector where we have a 1 corresponding to the token position and then a 0 elsewhere. But this is not a differentiable. This is not a differentiable function, so we can convert those into probability distributions by adding noise to the 0 elements and then normalizing those values. And so this one on the right is amicable to kind of reverse differentiation, whereas the one on the left is not. And then in the reverse process, we might see something like this, where we have a probability distribution of a particular token position being incrementally changed as we're performing the optimization, right? Even though our focus is only on MOF linker optimization, we still need a way to take into account contributions from the node and topology, and so we use kind of a more static encoding, so something like a token embedding, concatenate that onto our feature vector for the linker. And then we need a way to map this encoded representation to the property value of interest. As for this, we develop kind of a bespoke machine learning model comprised mostly of long short-term memory neural networks, which are designed mostly for it's designed for sequence to regression tasks. And these LSTM are comprised of 2 cells, which handle the differentiable and non-differentiable components separately. And then in order to kind of focus on different parts of the input sequence better, we apply a softmax self-attention mechanism to the LSTM outputs, and this is a feature that's inspired by ChatGPT type models, transformers. And then finally, to obtain a regression, an actual property value at the end of it, we have to pop it into like a regression head to compress it to a single output. And this is the essence of the approach, at least in the forward process. And so yeah, this model is capable of handling kind of more. It's capable of correlating the MOF strings to their property values with pretty good accuracy. Now, with our methodology for the machine learning model outlined, our first point of inquiry was to look at the void fraction or the volume fraction as a property value that has an optimization trajectory that's fairly intuitive to understand, but is still nonetheless important for carbon capture applications. So, you might want to increase the capacity of your material, and you might achieve this by extending the length of the linker, for example, to increase the void space. And so we might expect that a machine learning model that's designed to maximize the void fraction of a material might adopt a similar design strategy. And so we took our model, we trained it on some data in the forward process to predict the void fraction or the volume fraction even. And then in the reverse process, we tasked it with maximizing the volume fraction of some sort of seed structure. And so through continuous differentiation of the encoded input, you make incremental changes which result in pronounced transmutations of the linker within the real chemical space. So we're moving from a linker on the left-hand side over to the right-hand side. But of course, not all of these transmutations are valid from a linker chemistry point of view. We need the correct number of connection points between our nodes, and they have to be maybe appropriately distanced to encourage the formation of a porous crystalline structure. But nonetheless, we can see that in the valid transmutation pathway that there's an extension between the connection points of our linker, which we represent as francium pseudoatoms. So going from 7.39 angstroms between those 2 connection points all the way to 12 angstroms, which results kind of in an expanded pore space for our final optimized metal organic framework. And what's maybe an interesting outcome of this type of approach is that it lends itself quite nicely to more explainable AI, because we're looking directly at we're leveraging exactly what the model has learned in the structured property relationship in the reverse process. And we see similar strategies adopted at the kind of population level, where we task our model with optimizing hundreds of MOFs, so to achieve, to systematically shift the property distribution to higher volume fractions within the dream distribution. We then kind of wanted to look at a property value where you might be interested in maximizing or minimizing the property value depending on the application of interest. So we typically favor high specific heat capacity for pressure swing adsorption cycles or low specific heat capacity for temperature swing adsorption. So you might find either of these in carbon capture applications. And so we performed a similar population level analysis of the specific heat capacity, and we find that the model is capable of shifting the property distributions to values far shifted from the central tendency of the original seed distribution. And what's interesting is that the MOFs constructed from these linkers in the dream distributions are chemically dissimilar enough from the training distribution that we might be charting new and potentially interesting areas of the chemical phase space, and this is just based off of the mapping of the chemistry of these linkers onto 2D space. You can see 3 distinct regions, got the training set, and then the dream distributions as well. A caveat, of course, is that it's really easy to design materials in a computer without consideration of our experimental counterparts. And I think we lose credibility very quickly as computational scientists if we constantly generate something that no one wants to touch effectively. And so we kind of looked at the two synthetic synthesizability indicators for the linkers generated by our models. So synthetic accessibility and then the synthetic complexity. Lower values of these are typically preferred. You want something that's easy to synthesize or not very complex. And these 2 indicators point towards different outcomes, actually. The synthetic accessibility for some of the linkers dreamed by our MOFs are systematically lower than the dream distribution for the CPMAX case study. But then those same sets of MOFs computed by the synthetic complexity score seem to suggest that it's going to be very difficult to synthesize. If we operate under the assumption that the synthetic complexity score is the greater indicator of synthesizability, we find that optimizing under a constrained scenario kind of favors the formation of MOFs with linkers that are less complex, as given by the kind of like darker red distribution, which aligns more closely with the seed distribution and as well with the core MOF data set, while still achieving similar distributions in the property value as the CP, so in the very, very top right there. But these are still kind of proxy indicators for the synthesizability of MOFs, or they're proxy indicators to more rigorous definitions of synthesizability. Unfortunately, that's still a pretty open-ended and important problem, one that has not been fixed yet, but I think is fertile ground for some interesting research and ideas. So if anybody is interested in trying to predict synthesizability of MOFs, I'd be very interested to hear your thoughts afterwards. But just to summarize, I didn't want to get into too many details, but just to maybe provide some main takeaways from this work at least, is that we introduced deep MOF dreaming as a concept for inverse MOF design, which integrates property prediction and structure optimization into a single framework. We noted that deep dreaming can shift property distributions towards desired target values, and we observe improvements in both the individual and population level optimization scenarios, while still at the same time maybe providing interpretable insights into by observing by inspection of the transmutation pathways that we observe. But of course, more work is needed here to guide these pathways down synthesizable routes. So that's something that I'd be very interested in pursuing further if I had the time. But thank you, first of all, to my group with Lev Sarksov and all my group mates. Very, very many discussions about this. if you're interested, we've got the paper on ChemArchive, and the published version will be coming here any day now. So if you're interested, please have a look at that. And I'm happy to take any questions.